Good afternoon, this is Jason Letterman, and today's subject matter for the webinar will be air handling for all systems. Again, my name is Jason Letterman. I'm the air handling product manager for Titus TFX units. And today we're going to be joined by panel guests Jim Oswegen and David Pick. Today we'll be reviewing a few air handling configurations for a few different air distribution systems, as well as some specific sections you might need when configuring an air handling unit. HVAC systems installed in commercial and industrial applications have air handling units as a very important device. These units are important due to their supplying and conditioning air to meet particular needs in a given space. However, getting the desired results is not as easy to explain as describing the function of the air handling unit. These units are made up of many segments, each comprised of different components performing different duties. When designing air handling units, it's important to understand how segments can help or hinder other segments. The next portion of the webinar will discuss some of those segments relating to underfloor, displacement, overhead, and chilled beam applications. Overhead mixed air distribution makes up a majority of installed commercial buildings in the U.S. The simplicity of the air handling units includes a fan, coil, filter, and intake section. Controls of a standard overhead air handling unit are fairly straightforward. Coil capacity is controlled by leaving air temperature to maintain set point. The variable air volume fans are controlled by duct static pressure sensors and VFDs. Units can be controlled with primary duct static pressure resets per ASHRAE 90.1. In this configuration, the BMS will poll the configured terminal units and provide adequate static to maintain the minimum static required to meet capacity. The mixing box can be controlled as a simple static setting or provided with modulating dampers and actuators to allow demand control ventilation per ASHRAE 90.1. A mixing section with actuated dampers can also be used to provide a system with an air side economizer. To kick things off, we'll look at the Plenum and double-wide house fan applications. Plenum airfoil fans offer superior performance for many applications. Typical concerns with the fan performance are efficiency, noise, and air velocity profile through components. Plenum fans offer advantages for all three concerns. Additionally, the fans provide flexibility with outlet configurations, reduced mechanical space footprint, and the benefit of direct drive. Efficiency is typically found for the double-wide house fans due to the use of the scroll to increase their efficiency. However, optimizing this fan requires a process referred to as static regain. Housed fans are tested with an outlet duct of 2.5 to 3.5 times the wheel diameter in length. This outlet duct allows the static regain process where velocity pressure is converted to static pressure. Housed fans applied without the outlet duct will require a system effect factor, which decreases the overall fan efficiency. Housed fans in blow-through positions will also require an air diffuser, which decreases the efficiency further. The combination of these two system effects brings even the best housed double-wide fan efficiency to or below that of the Plenum fan, thereby eliminating the benefit of a fan scroll. With regards to noise, Plenum fans have the benefit of effectively utilizing the entire unit as a fan housing, which offers superior attenuation. The system factors that decrease the housed fan's efficiencies discussed above also increase the noise level of the housed fan. Also, since a Plenum fan has no scroll, typically means larger fans can be installed in the same size cabinet compared to the double-wide double-inlet fans, which generally produces better sound characteristics in those applications. For design pressures at or below 6 inches water column, it is very common to see supply air sound power levels lower when using a Plenum fan instead of a double-wide housing fan. Additionally, perforated liners may be used in Plenum fan sections for greater attenuation. Lastly, velocity profile. Due to the relatively small outlet blast area of a double-wide fan, an air diffuser must be applied to the discharge of the fan to obtain an acceptable velocity profile through the next component. Air diffusers add static pressure which decrease fan efficiency and increases fan noise levels. Plenum fans positively pressurize the entire cabinet. They do not require a diffuser and its associated performance losses. Some other characteristics of our fans may concern the outlet flexibility. Plenum fans serve to pressure the entire fan plenum, allowing for multiple duct takeoffs from the air handling unit. Additionally, these openings can be tailored to match virtually any duct configuration, whether it be rectangular, round, flat, oval, with a bell mouth fitting, just to improve the acoustic and optimize pressure drop performances. When it comes to mechanical space optimization, a housed double-wide fan requires a straight run of duct per AMCA guidelines at the outlet of the fan before elbows can be applied. This constraint imposes restrictions on duct layout and mechanical space design, which generally increases overall footprint requirements. The ducted takeoffs from pressurized plenums, as in the case of the plenum fans, does not have a requirement for a straight run and affords greater flexibility to the architect or engineer in ductwork design. Lastly, we'll take a look at the direct drive benefits. Specialty double-wide fans can be used in direct drive arrangements where the fan wheel is directly mounted onto the motor shaft, and most typically housed fans are driven by a belt and shift system. Belt drive systems typically allow for 3 to 5% of efficiency loss and impose maintenance requirements not present in direct drive systems. Additionally, belts wear and give off debris in the form of belt dust. Any more discerning engineers apply direct drive plenum fans with VFDs for efficient variable volume duty and trouble-free maintenance. Our next component is the cooling coils. When selecting cooling coils, there are a couple of rules of thumb to help you with a quick design. One is the velocity limits across the cooling coils. Face velocity over coils is generally limited to 500 feet per minute as a maximum. There are a couple of reasons for this limit. One is moisture carryover. About 500 feet per minute condensate from the coil fins and tubes can be carried into the airstream over the drain pan. A good design starting point is 450 feet per minute. At this point, the unit can be turned up an additional 10% without running into carryover concerns. Additionally, velocity across the coil equates to the pressure drop. Lower velocity helps to minimize the unit pressure drop and thus motor horsepower requirements. The depth of coils relates directly to the latent capacity and fan power. Minimizing the number of rows in a coil would decrease coil pressure drop, but at a penalty to coil latent capacity. Generally, we would expect to see 4 to 6 row chilled water coils used to handle standard office air handling equipment, but would expect to see 6 to 8 rows for an outside air application. As the depth of the coil grows, so does the difficulty in cleaning the coil. Filter sections are provided upstream of cooling coils. In many installations, the filter section is utilized as the intake section of the air handling unit, foregoing the mixing box section. In the upcoming slides, we'll look at the V-bank filter configurations and the effects they have based on their placement. There are some more commonly found design principles applied to air handling units, and they're addressed in the ASHRAE 62.1. The first one we'll take a look at is ventilation for acceptable indoor air quality. Section 5.8 states that a minimum of MERV 8 filter be provided upstream of every cooling coil designed to or operated to condense. This is a minimum standard. Best practices generally include a pre- and final filter application. Another topic may be the call for access doors or panels for cleaning sections. Mixed air plenums and upstream surfaces of each heating, cooling, and heat recovery coil, or possibly coil assembly having a total of 4 rows or fewer, should use some form of access, while upstream and downstream surfaces of each heating, cooling, heat recovery coil having a total of more than 4 rows, along with air washers, evaporative coolers, heat wheels, and other heat exchangers, shall have access doors applied. As you may recall, we briefly touched on the use of mixing and economizer boxes. Mixing boxes and economizers play a starting role in many air handling unit configurations. The mixing box is a section of the air handling unit used to mix the return airflow with the outside airflow. It consists of two dampers whose operation is coordinated to control a fraction of the outside air in building supply, while maintaining the supply airflow rate constant. There may be two different ways of incorporating mixing boxes into a system. The first is simply within the air handling unit, or the second, which is applied to the ductwork. The ductwork install may serve its purpose when two separate ducts are not capable of being connected at the air handler. Much like the mixing box, an economizer segment includes dampers for outdoor air, return air, and relief air. These dampers are controlled to provide airside economizing. Many commercial buildings have spaces which use cooling all year long. If outdoor conditions are favorable and temperatures are below the return air temperature, it often makes sense to save energy by increasing outdoor airflow in lieu of recirculating return air to reduce mechanical cooling. In healthcare facilities, economizers are great energy-saving options due to 24/7 facility operation. So when running at night, economizers can serve the building by using cool night air. Using increased outside air should encourage a healthier environment for patients by reducing the use of recirculated stale air and reduce runtime of compressors, pumps, chillers, and condenser fans on refrigerated units. Economizers can extend the life of your HVAC system and components. We'll now look at the V-bank filtration in air handling units. As most know, V-bank filter arrangements reduce filter velocity and filter pressure drop by up to 60%, saving energy. The arrangements provide additional surface area for particulate removal, but they also extend filter life expectancy by as much as 4 times. In the next few slides, we'll focus more on the placement within the air handling unit and how they affect other segments. Most, if not all, coil applications look to incorporate filters into the air handling unit for cleaner coils, allowing them to operate more efficiently. We also know with mechanical rooms, space is sometimes limited. To reduce overall length, we place filters inside mixing boxes and economizer segments. Placing air filters in these seemingly unused spaces causes significant reduction in mixing effectiveness. Let's take a look at a few different layouts using V-bank filters. Let's start with a V-bank filter inside of a mixing box. In this particular configuration, we see a 45% mixing efficiency, while our lowest temperature at the coil face will be 28 degrees. Now let's shift the filter section back in the unit, giving more space to mix the two air streams. We now find our mixing efficiency has increased to 55%, while the lowest coil face temperature reads 32 degrees Fahrenheit. Note, when space is available and increased efficiency is needed for mixing, shifting the filter location back into its own section could be the best option available. A third option is the use of a blending section. I'll cover a little more info on blenders in just a few moments, but let's look at how they affect our mixing efficiency and coil face temperatures. By adding a blender section, we see the increase in our mixing efficiency to nearly 80% and our coil face temperature jump to 45 degrees Fahrenheit. Adding a blender section provides better mixing and diffusion across the filter and the coil downstream. Though preferred, incorporating blenders and filters into a unit may put a squeeze on space availability in their air handling layout. As seen in the previous slide, the blender section can provide additional benefits to mixing boxes and economizers. By definition, blenders are mixing devices fixed in position consisting of baffles and blades used to induce mixing to the flow of air. The next few slides will show some of the functions of the blender segments. Blenders such as the one shown in this slide provide freeze protection of hydronic coils by continuously mixing the cold outside air into the warm return air from the building. Generally, blender operation requires roughly 400 feet per minute or above for it to operate properly. Additionally, the device provides a degree of flexibility during unseasonable heating and cooling trends during seasonal changeovers, when chilled water cooling may be called upon. In addition to freeze protection, the blender can solve problems created by stratified temperatures in the mixed air plenum, such as mixed air sensor air or uneven distribution across filters and coils. So where do blenders fit into the scope of hydronic coil protection? In the scheme of things, blenders show a high level of promise in all categories except shutdown, of which shutdown procedures should exist, ensuring coil safety from freezing temps. A blender is the only option that provides freeze protection without the need for maintenance. Our next segment will be staggered coils and blenders used within them. There is a time and a place to use staggered coils to increase coil face area and allow increased CFM without having to increase cabinet size. There may even be a case where you might need some type of coil redundancy. One byproduct of staggered coil arrays is the formation of stratified temperatures downstream, causing issues for the discharge thermostat. A high reading may cause the pump or condenser to operate longer and lead to coil condensate issues, while a cold reading will cause a higher supply air temperature. Another possible issue with staggered coils is downstream stratified air being pulled into the inlets of a double-wide fan or a multi-fan arrangement, and not properly mixing before being discharged into multiple ducts. This condition could bring bigger issues with control of the unit and comfort problems for those demand areas. Wrapping up our last example of blender segments, we'll look at the internal face and bypass segment issues controlling the discharge temperature downstream of the face and bypass coil. The primary cause in temperature differences is the general location of the bypass air and the coil leaving air temperature. Because bypass air is typically found on the top or bottom of the coil, the temperature difference between the coil and the bypass air causes stratification. The blender serves the means of mixing the two air streams to assure proper control of damper modulation. Understandably, everything included in the design of an HVAC system has a purpose to optimize the quality of the system and reduce maintenance. As a target, engineered designs strive to reduce cost without reducing the functionality of a system. Eliminating a blender represents a minimum front-end savings but significantly reduces air handling unit functionality and not realizing energy savings. This chart highlights the segments discussed in previous slides to help optimize your AHU designs so that your next project has a higher level of performance and reduced cost. Moving into our next segment, ASHRAE Standard 62.1 suggests maintaining a relative humidity of no less than 30% to provide a comfortable, healthy indoor environment. Depending on your proximity, humidity control can mean several things, as well as several different methods of controlling. The next section will primarily focus on the humidifier segment only. What are the types of humidity control? Isothermal systems use heat from an external source to create humidity. Electricity, natural gas, hot water, and boiler steam are used to boil the water to create steam. Adiabatic systems use heat from the surrounding air to change water into vapor for humidification. Since we've identified a couple types of humidity control, we can now look at considerations in optimizing our selections. To start our considerations, we use horizontal airflow for dispersion. We also limit the housed blow-through fans due to issues with turbulence within the air handling unit. We also maintain uniform velocities at the point of humidification and using roughly 400 feet per minute as a starting point. The proximity of the humidifier segment should not be located upstream of filters, cooling coils, gas, or electric heat. With regard to proximity, changes in direction of airflow, for example, in a vertically configured air handler, may require larger segments immediately upstream and downstream of the humidifier segment, affecting the overall footprint in the mechanical space. Providing factory-installed equipment within the air handler lowers the cost of field installations of the humidifiers and keeps moisture out of the supply duct. Today, people spend more time indoors than ever before. It has been proven that air we breathe can make us feel unhealthy, deficient, and tired. This, in fact, does affect our well-being along with our productivity. People expect the air they breathe to be reasonably safe and comfortable, yet indoor air can be laden with mold, mildew, dander, bacteria, and other viruses. As a result, many owners and engineers are turning to ultraviolet disinfection to meet this new and emerging requirement. Ultraviolet light has been utilized to disinfect surfaces as well as a variety of liquid applications, including drinking water. The UVGI process is utilized on makeup water for juices, sports drinks, and a variety of beverages you encounter every day. Another popular application for ultraviolet disinfection is treatment of processed water utilized in a variety of industries, including pharmaceutical processing, semiconductor rinsing, and boiler feed. Many manufacturers develop UV options that will utilize UV lights to control airborne and surface microbial growth and transfer. These two options are surface decontamination and airborne inactivation. Surface decontamination is designed to treat the surface of the cooling coil and drain pan of the air handling unit. UV lights are attached to mounting brackets installed in the coil segment in such a way that the coil and drain pan are continuously exposed to the UV lights. UV lights in this option are normally placed downstream of the cooling coil or drain pan. In this application, reflectivity of the UV light is of dominant importance. Any increase in reflectivity enhances the UV effectiveness and efficiency. The kill rate increases dramatically with this option since exposure time is unlimited. This is important since mold and other spore-sized organisms have a much higher kill threshold than bacteria or viral contaminants and require a longer exposure time to kill them. Applying this option to the AHU doesn't warrant much space claim and typically can be configured in the cooling coil segments. The airborne inactivation option is a standalone segment specially designed to attack airborne viruses in moving airstreams. This segment can be installed upstream and or downstream of all cooling coil segments. The UV lights are configured in such a way to kill or disinfect microbial agents as the air moves past the UV lights. For a moving airstream, we only have a limited amount of time to attack the microbes, so we must adjust the UV intensity. We do this by applying higher output UV lamps to increase the intensity output. For an on-the-fly kill application, many more variables must be identified before we can determine which UV design will properly treat the moving air stream. Using this option, a reduction in airborne organisms can be rapidly achieved. Air entering the air handler is subjected to radiation at the time of entry. The airflow can be disinfected up to 99.99%, depending on the number of lamps installed, length of time of exposure, and the dimensions of the air duct. A key aspect of this option is the fact that some pathogens may be too small to be trapped by the HEPA filters with 99.99% efficiency, but they are very susceptible to the effects of UV. The full air cleaning provided by this combination of HEPA filtration and airborne inactivation also achieves a disinfecting effect on local surfaces. Typical applications of this option are found in laboratories, food and beverage, cosmetics, or pharmaceutical industries. If both surface decontamination and airborne inactivation options are used together, they can virtually clean your unit and the air you breathe. Working together with various filtration systems and complying with the requirements of ASHRAE Standard 62.1 will assure the best possible indoor air quality when the designer combines all these technologies. With our recent overview of different segments and their function within the AHUs, we can jump back into some of the air handling unit configurations, and the next one up for discussion is the underfloor air handling units. Our second air handling unit configuration for discussion is underfloor air distribution, as well as building on the basic unit with some added features. The air handling system needs to provide dehumidified air just as an overhead air system, but at warmer discharge temperatures. To optimize energy savings, this needs to be done without using a reheat coil. So what's the solution? How about the internal and external bypass segments? Let's reference the underfloor application for a moment. For occupant comfort, discharge air temperatures are generally in the range of 61 to 65 degrees Fahrenheit. These are warmer than overhead leaving air temperatures, which range between 50 and 55 degrees Fahrenheit. Dehumidification is a necessary process to maintain occupant comfort. If you look at the psychrometric chart, you will notice that 61 to 65 degree range will result in an unacceptably high relative humidity in the occupied space. The previous solution to this problem was to cool all the air down to overhead supply air temps and then reheat. This would then allow adequate dehumidification at warm enough supply air temperatures to maintain occupant comfort, but at a considerable energy cost. The solution to avoid using new energy for reheat is to provide a bypass. By cooling some of the air below dew point and then mixing it with return air to the desired supply air temperature, now the humidity is handled as well as the comfortable supply air temperature without using new energy for reheat. When designing an underfloor unit, it is worth mentioning that all the humid outside air should be directed through the cooling coil and only return air used for bypass. This will help minimize space latent loads by preventing additional humidity from being introduced into the space from an outside air through the bypass section. To address this concern, external bypasses work best. The outside air is directed into the mixing section of the unit. The desired amount of return air is then introduced downstream of the cooling coil to mix with the supply air temperature up to desired levels. The remaining return air is discharged into the mixing section with the outside air. When using an internal bypass, the unit will be fitted with face and bypass dampers. The dampers control airflow and modulate supply air temperatures by bypassing around the coil. Things to consider when sizing the cooling coil and bypass: attention should be paid to the cooling coil to make sure it will provide the required latent cooling at less than 100% airflow of the unit, to allow adequate bypass air to mix up with the minimum supply air temperatures. Face dampers for cooling coils are not always required. The airflow through the coil will be considerably higher than through the bypass section. Also worth noting, pressure drop of the cooling coil will increase with latent capacity. A 100% sensible coil has a lower air pressure drop for the same face velocity as a coil with latent capacity. The reason for this is that the air tunnel through the coil is decreased due to the condensation between the fins. The manufacturer should provide selections at different entering conditions to determine dry and wet pressure drops. The designer will also need pressure drops across the bypass at different airflows to verify the need for cool face damper. With regards to controlling the units, the cooling coils are controlled by space humidity, while their variable air volume fan is controlled by floor pressure. And the bypass section will now control supply air temperatures. Air handling units for displacement systems can be very similar to underfloor air distribution units. Depending on the design of the displacement distribution system, if 100% of the supply air of displacement system is supplied from the air handling unit, it can be constructed and controlled very similar to the underfloor unit. The control sequence is as follows. Cooling coils are now controlled by the space humidity. The variable air volume fan is controlled by the duct pressure. The mixing box controls stay the same. And the bypass section will now control supply air temperature. If cooling and dehumidification are provided from the air handling unit and discharge air temperature is controlled by mixing at the zone, then the air handling unit will be more of a standard overhead system, but with a reduced footprint and airflow. Air handling units in a chilled beam system provide the following functions. Primary air at a medium pressure to the beams to drive induction and space cooling. It also serves as dehumidification to meet the space's latent loads and ventilation air to the occupied space. Chilled beam systems provide energy savings through reductions in transport energy. It is more efficient to transport BTU per hour with water than air. To do this, these systems use the least possible airflow to maintain space conditions. The primary airflow is based on a required supply airflow for chilled beam induction to meet latent capacity and outside air for ventilation. In most cases, supply air for latent capacity is the greatest of the three. During peak cooling hours, outside air generally has the highest enthalpy and thus requires the most energy to cool and dehumidify. For this reason, buildings with high humidity loads should mix return air with outside air to provide additional latent capacity in minimizing energy consumption. Other methods of decreasing air handling unit energy is by use of heat wheels. A two-pass heat wheel will pre-cool the incoming airstream prior to the coil, allowing the cooling coil to expend more energy on the latent cooling side. After the air is cooled and dehumidified by the cooling coil, it will make a second pass through the heat wheel. The air will now be cold and close to saturation and will now pass moisture to the wheel while cooling it and thus dehumidifying the supply airstream further. The energy expended for the additional dehumidification will be minimal along with the pressure drop across the wheel and the energy to turn it. The coil must be sized to maximize latent capacity, or another way of saying it is to minimize sensible heat ratio. This can be accomplished by deeper coils moving air at decreased velocities, and the deeper coil at a lower velocity allows the air to stay in contact with the cooling surface longer, which allows more water to condensate or condense out of the air stream and thus increase the latent capacity of the coil. The heat wheel has a bypass to allow the wheel to be bypassed when conditions are not favorable and minimize air handling unit internal pressure drop. For these units, it is also provided that a heating coil is provided for freeze protection. The controls for this configuration are simply put as the cooling coil is controlled by the humidity, the fan is controlled by the duct static pressure, and the band control ventilation controls are on the outside air. A second configuration for chilled beam air handling unit combines a heat wheel being used for energy recovery. This heat wheel transfers sensible heat from the outside airstream to the building exhaust airstream in cooling. It also transfers moisture from the outside airstream to the exhaust airstream in cooling. In the heating process, the work is reversed, reducing the preheat energy and helping to maintain minimum humidity without the use of new energy. Today's escalating energy costs have demanded high-performance air handling units. Air handling units with optimized segment layouts using energy-efficient components and specific design configurations will allow modern buildings to be much more efficient. The low-energy, high-performance air handling units reduce the cost of ownership. Energy-efficient equipment also increases the asset value of a building via recognition from the U.S. Green Building Council and by providing greater occupant satisfaction and/or productivity. As you've seen in this session, the quality of products, manufacturing practices, and application-specific designs used in today's air handling units can overcome a higher first cost and ensure energy efficiency.